I will briefly talk about what we are doing, what TomTomers do with data science and AI, just very briefly. And then I will talk about message-centered data, the techniques and the methods we have while we wanted to work with sensor data. And I'm going to point out just one of the challenges I've been facing. And that will be it. And then you can have drinks and say goodbye. All right, let's start. We are TomTom, and we are actually a location technology specialist. We are shaping mobility with software, navigation softwares, highly accurate maps, and real-time traffic information. At TomTom, our vision is a safe, connected, autonomous world without emission, without congestion. And we are revolutionizing mobility as we know it, and that's what we do. And we believe in keep the world moving. And from data science point of view, I'm going to show you what is our recipe to keep the world moving. So every data science, our recipe as data scientists, our recipes are start with ingredients, which is, in our case, is data. We get the data, we apply analytics, advanced analytics from descriptive analysis, basic analysis, and all kind of machine learning and deep learning. We leverage those things to extract insights from the data that helps our product team, our stakeholders, to make better decisions, to get closer to their customers, and by creating features that make the ride of the users more enjoyable and safer. What data we are actually owning? So we are location specialists. So basically, we are owning one of the biggest GPS traces databases in the world. Every day we are getting 742 million kilometers driven by the users of our application, of our users. And yeah, and this is the image that you show here, that I have here, is the probe data from Europe. But it's not the only data that we are working on. We are actually having data sources from community inputs, traffic sensors, car sensors data, and the image that you see here is the TomTom Momo vans. They are actually equipped with different kind of sensors, with well-positioned video cameras that they can actually collect data, and they are driving all over the world to collect the data. Well, we are a big organization, from maps, autonomous driving, road trips, mobile applications, driver apps, navigation, traffic, and this is a big organization. And each of these departments and product units, basically, they have data scientists and the AI specialists that they are working on these kind of data to extract features and create amazing features for the users. And well, actually, I'm not able to cover all the amazing stuff and cool stuff that my colleagues are doing, because some part of it is confidential and some part of it is because I cannot cover it in half an hour. But I'm gonna just show you an example of one of the very amazing things that my colleagues in autonomous driving team are doing by leveraging the deep learning and neural networks to create highly accurate maps for autonomous drivers, autonomous cars. All right, but I'm just showing you a tip of an iceberg. This is not only things that we are doing. Okay, I bet some of you have seen these images. These are, at one glance, they are just, image of people, normal people, just smiling, have different impressions. But this is fake. They are not real people. These are the images that are created by generative adversarial networks, GAN for short. Basically, these are the networks based on a game theoretic approach that a network learns to generate learns from the training and tries to generate data points and observations that are really real looking. And so it is a game theoretic base. So you can see that these networks has two players, generator and discriminators, and they are in a constant battle in the training process. The generator tries to, by adding some random noises to the real faces, generates images and faces that are real looking, and the discriminator cannot detect them as fake or real. And so these, well, actually, it's a very cool application of neural networks. And using GAN, actually, if you give the network a segment of image segment of the road, it can actually add more details to make the image more real by adding, for instance, cars, lanes, and trees and everything. And my colleagues in autonomous driving team, they have proposed a framework based on GAN that tries to actually improve the training, the predictions for the lane detection. Basically, this uses intuitively, not in scientific words. It tries the generator tries to the discriminator tries to look at the predictions and also the training labels to increase detection accuracy or reduce the numbers of the images that it misclassifies. And for instance, this is just one of the things that you can see. This is a just illustration of how this approach works on lane marking segmentation. This is a ground truth of the road, and these are the red lines are actually lane. And this is just the one that is create prediction of the lanes based on a network, a neural network. And this one is based on LGAN. And you can see that this is actually, it's really well preserved. It's very similar to the ground truth. And actually the lines are very thin, so you can see that this is highly accurate and there are less uncertainty there. But so if you actually want to know more about this, you can just, at the end of this presentation, you can scan this QR and go to the page of the paper and enjoy reading it. It's a very nice paper. Well, as I said, this is just the tip of an iceberg. We have superheroes in other teams that some of them are actually sitting there here. And they are doing a very cool stuff with data and AI. All right, let's get serious. Messy sensor data. The first thing I can tell about sensor data is that they're everywhere. We are kind of living a golden age of sensor data. All the devices that we are carrying every day, from mobiles, computers, smartwatches, cars, and even refrigerator or the microwave that's sitting in your kitchen, they come with different sensors for different purposes. And well, actually, we are surrounded by these sensors, and they are impacting every aspect of our life, from all the kind of sensors that you can see in these devices to manufacturing units. Everything is getting smarter and smarter every day. But some of these devices are actually sensors are expensive to deploy. For instance, not all of the cars on the road they come with sensors, or not all the homes are smart with all the devices with sensors. But one thing that we actually never leave is our smartphones. We are going to the toilet with them, we're going to the bed, we are taking shower sometimes. Not we, but some people. And I'm not judging. And these are the things that actually we are not leaving the house without our smartphones. And they are already equipped with different kind of sensors for different purposes. And I'm going to just show you that how insightful these sensor data could be. But sensors and sensor data are kind of abstract concept. Let's walk through the common sensor that you can find in a smartphone. So, first of all, the GPS sensor that I believe that everyone actually knows about GPS. And this is a sensor that indicates where are you and where you're heading to, and it gives you information about the location. And I think there is no need to mention that GPS is a source of incredible insights about where you are now, where you are going, and even what kind of person you are by just looking at what type of trips you are taking, or where you are spending most of the time, or places you are visiting. The other sensor is magnetometer, which is actually plays the role of a compass to your smartphone and indicates that where are you in the space regarding the orientation of your phone. The other two sensors is accelerometer and gyroscope that are referred to as motion sensors, and together with magnetometer, these sensors forms your IMU, inertial movement unit. And actually, let's focus on these motion sensors for a little bit. Accelerometer is the sensor in your smartphone that indicates when you are switching between portrait and landscape. And it measures the acceleration that your phone is experiencing in 3 axes: up and down, left and right, back and forth. And the other sensor is gyroscope, which is introduced by Apple for the first time in iPhones, and is there for the gaming purposes. And it measures the rotational velocity that your phone is experiencing. And for instance, when you are playing games like driving and you are moving your phone, it is the job of the gyroscope that indicates when to go to left and right. All right, these motion sensors can indicate that where can give you highly accurate information about the position of the phone. For instance, if it's in your hand, if it's in your pocket, or those kind of things. And I'm going to actually show you some applications of motion sensors, and show you that by tapping the potentials of smartphones, you can make impact. So applications, and who are actually interested in them, apart from me. So one of the well-known applications of sensor data and sensors are activity recognition. Basically, it can detect when, from the reading of accelerometer and gyro, you can say when someone is walking, running, cycling, or driving. And who is actually interested in this? It's health tech companies, basically, and wearing tech industries are actually interested in knowing that how they can automatically detect different type of activities that you are doing while you are having your smart watches with yourself. And the other application is driving behavior detection. Assume that you have your phone with yourself in the car and you want to drive. So if the phone can be in a car kit, in a windshield, or it can be like mounted in a car kit but on the CD player, and you are driving. The readings of the accelerometer and gyroscope can detect what type of driver are you. Are you a careless driver? You are just changing the lanes, you're accelerating, you're harsh braking, or what kind of behavior you have. And actually, insurance companies are really interested in knowing that what type of drivers are you. Are you a risky driver or you're a safe driver? And basically, yes. And most of the insurance industries are transitioning from fixed fee packages, insurance packages, to a usage-based insurance packages. It may happen to you that when you buy a car, some insurance companies, they are offering you to deploy some sensors in your car that they are actually analyzing your behavior, your driving behavior, and in return, they offer you some discounts on your packages. They are all because they wanted to analyze and collect data on their driving behavior. And so there is another actually interesting application of sensor data. So there is a proof of concept carried out by IBM and a team of researchers from Pennsylvania University that they created a Trojan app that abuses the motion sensors and detect what keys you are tapping while you are entering your credit card information while you're e-shopping. So it all, I'm just pointing out some examples of the applications of motion sensors to just show that there are actually a real potential insights in these sensor data that you can actually, they're waiting for us to harness the value of them. All right, but we are all about, talking about sensors and sensor data. Let's see that how they actually look like. So what I'm showing you here is the accelerometer reading of my phone while typing. So actually you see that those those white tops and downs are actually when I tap a key. So I just had the phone in my hand like this, and I was typing. The other reading is while I was walking. So it is, let me play it. It was like this. And you can see that the movements that I have, like these periodic movements, you can see some patterns when the three readings are coming closer to each other. And the other one is when I was driving, and the phone was in a car kit, in a windshield. It's installed in the center of the windshield. And I was actually not accelerating. It was like 50 kilometers. It wasn't like more than 50 kilometers. The speed wasn't more than 50 kilometers per hour. And it is still, very noisy. And my phone holder is kind of steady, but it is already, noisy. And there are some messy patterns. I don't know if it's in there or not. That was like when I turned right. So some of the patterns that you are driving, and for instance, you are turning right or turning left, your harsh braking, or all kind of things can be read from sensor data. All right, now that we know what is the value of sensor data, so assume that you collected the data that you want to work on, and you set your objective. For instance, you want to classify the different activities that you are doing based on while you are carrying out your phone. What are the steps and you want to take, and what are the tools you have in hand to work with these kind of data? Well, I'm going to review those things from now. So it starts by data preparation. So every data-related journey starts with cleaning up the data and make a better sense of your data set. And if you are, actually, depends on the quality of the data. If you're lucky, this step could be like a piece of cake. But most of the time, it's not. So most of the time, what we get from the data is like a bunch of garbage, and you want to just clean it up and get some valuable data from that. And when you're working with signals, it is actually more, painful. The first thing that you want to ask, and the main question while working with sensor data, is signal or noise. So you wanted to know that what is valuable in your data, what is actually like a random noise, or what is valuable and what kind of information you can get from your data. And when people are talking about signals and sensor data, you just expect, to see a very nice periodic, sine wave-like pattern. And if you are lucky, and believe me, if you're lucky, you're going to get this. And you're just like Sheldon Cooper from The Big Bang Theory, just freaking out how you feel, and how you wanted to do, what you can do with this data. But there is no need for freaking out, because it is always like this. The data is always like this. One thing that I have actually learned while working with signals and these kind of data is that you need to think simple and be creative in the techniques that you are using. For instance, if you are, and you can just remove unwanted samples that shower your data, and these small steps can give you a better quality of the data. For instance, if you are interested in reading of the sensors while there is a movement, you can just use another sensor like GPS and extract the speed from there, and then you can apply a band pass, a low pass or high pass filter on that, and just only get the values, the observations that there is actually a movement there. And if you are, for instance, working with only accelerometer and you wanted to know when you are turning and you cannot make sense of the data, you can combine this with the gyroscope, and together with combination of the sensors, you can already get a better sense of your data. But if none of these things works, you can always use denoising techniques. You can use the thing that you see here is the denoising of the signals using wavelet. And so I'm going to just explain intuitively what is it. So if I bet that everyone knows what is a sine signal look like. It goes forever. But wavelets are actually mini waves that they start, they burst, and then die away. So instead of, if you want, for instance, get rid of these very small vibrations to just get a cleaner data, you can use the wavelet for denoising. It actually decomposes these signals into mini waves, and then actually the summation of those things, I'm just talking about not in an exact, in an accurate mathematical formulation. It actually gets rid of these up and downs. But this is not the only technique that you can use. There are Kalman filtering, and you can use a fast Fourier transformation. There are different libraries, and actually they're well-shaped libraries for Python that you can use for denoising the data. And it all depends on your data and how much information you want to lose or you want to gain. Because denoising means that you are actually losing some of the samples, and it depends on actually your use case. All right, after preparing the data, it comes to the method that you can start modeling your data. So if you, for instance, you have a classification or a prediction. So what you can try is two types. In general, working with sensor data and signals, we have two options. You can go with the statistical models, or you can go with machine learning-based models. And I suggest whenever, well, actually, the answer is not always, a complicated neural network. Sometimes statistical models and time series-based models can do the job, and you don't need to, go straight forward to trying a neural network and try, for instance, do the anomaly detection. First, try to just understand the data and understand, how statistical models, what is the drawbacks and what is the weak points of these models, and how we can improve this using machine learning and neural networks. And I'm just going to show you one of the well-known techniques in a statistical model, which is a time series based, and this is called dynamic time warping, which is actually measures the similarity between two signals, how similar these signals are. And it is good if you wanted to, for instance, if you're looking into some patterns in your signals and you have the reading of, for instance, about records of a million time series, and you can actually use dynamic time warping to just cluster those things that they have a similar pattern and they follow the things. And how it works, and just to mention, if you are familiar with Levenshtein distance for autocorrecting words, basically dynamic time warping is the Levenshtein distance for time series, and it can be used for speech recognition, I guess. It's a very popular technique. And how it works is, when you wanted to, for instance, an Euclidean matching is that when you have two signals like this, and you are actually mapping one-on-one between each point from red to blue, and you don't know what to do with this, if they are not synced or they don't have the same length, so Euclidean matching is not working. And then dynamic time warping tries to to make a non-linear mapping between the points of a red plot and the blue plot, and by minimizing the distance. Going through the details, and so let's see that what else you can try. Machine learning models, and when we say machine learning models, I would say like standard and traditional machine learning model like support vector machine, random forest, and so on, and there is a deep learning. So my suggestion is if you are not certain that what kind of features you wanted to use for your signals to do your, for instance, classification or prediction, you can use, and if you have enough data points, then you can use neural networks. But if you don't have enough data and you are kind of sure that what features would work, then I would suggest to go for traditional way of detecting or classification using machine learning. And so if you wanted to choose this and not deep learning, then you have to do feature engineering. You need to extract some features from the signals. And there are two types of features you can extract from the data. One is time domain-based features, and the other one frequency domain features, which are actually time domain features actually summarize the information, the statistical information in the values of the data. So this is, we have like this is the time and this is the values. And what you can do is that it depends on actually your sampling rate. If you are sampling the data on high rate, for instance, if like 100 samples per second, then it is like your data is already noisy. And maybe the single points of the observation are not something that you are interested in, but you wanted to know, for instance, what happens in for instance, 5 seconds or in 30 seconds or something like this. So what you can do is you define a window of length, for instance, 30 seconds, and then with some overlapping ratio, that if you want to, for instance, do the labeling, these overlapping actually, so this is some simple remedies to reduce the error that you have for labeling, more manually labeling the data. And then you can extract, for instance, the average value of the signal here in that window, a standard deviation, mean or max. These are actually usual things that you can extract. And what about the other features? Nikola Tesla says, if you want to know the secret of the universe, think in terms of energy, frequency, and vibration. And that's what we do, because you cannot say or question, what Nikola Tesla said. And so we are going to extract some frequency domain features. And actually, intuitively, you want to understand what is going on from what kind of frequency information exists in your signal. And so actually every signal that you can see, there are like A, which is amplitude, the period of the signal, which is like, phi is the phase, and omega is like a period of your signal. And then you can use fast Fourier transformation. What actually fast Fourier transformation does, it says that all the periodic and non-periodic signals can be decomposed into a linear combination of sine and cosine. And actually, what you can see is the contribution of, so this is the signal that we have, and this is the decomposition of these signals in terms of sine and cosine. And what you can see here is a contribution of, intuitively, is a contribution of each signal. It's each cosine or sine signal. And then from this information, you can extract, for instance, the energy of the signal. And again, intuitively, it means that how much energy you need to create that feature, with that signal with that frequency. And also, you can create, you can extract entropy aspect of your signal, which indicates that how much information exists in your signal. So if it's a noise, then there is no information, which is a high entropy. And if it's like actually the real sample that you want to use, it is actually the low entropy and more information. For instance, if you are recording a sound in the room and you're just dropping, it's like silent, and you're dropping something, this one can be detected as a noise, because this is like something that is like outlier somehow, and it indicates a very high entropy in your signal. And it can be detected as like something like outlier. And when you actually do this feature engineering, you can feed these features to, after some feature reduction, normally, then you feed this data to your machine learning model. It could be random forest, support vector machine, and then do the classification, prediction, or whatever your objective is. All right, this is just the method that we have, and now I'm gonna just show you one of the challenges that I had, I'm having actually, while working with motion sensors. So all the sensors that you can see in your smartphones are basically they work based on the coordinate system of smartphones, which is actually Y, so it is the X, which is the X, Y, and Z. But this, actually, the phone can be in any orientation in the car. So I'm interested in knowing, for instance, detecting some events while people having their phone on in the car. But this phone, I cannot impose, anything to. I cannot ask anything from the user that you should put your phone in this position, because they need to actually do whatever they want. So for what we actually need is that we wanted to fix a coordinate system and then transfer everything that we have into that coordinate system. So we need a reorientation of the phone in any direction that it has. It is something that actually this is one of the practical things that you need to take care of when you're working with smartphone motion sensors. All right, this is just one challenge, and I don't have time to go through all the challenges that I'm having. And so I'm just gonna close it. But so the new rule of the future, as Jacob Morgan says, is that everything that can be connected will be connected. I haven't mentioned anything about IoT here, but you can think about, that we are actually carrying our smartphones everywhere. Everyone has these smartphones that they are actually sensors, and reading of these sensors, different sensors that you have in your smartphones. And you can think about it as like a mini IoT. And basically, there are many potentials in there, and you can tap. Actually, as I already mentioned, that you can tap the potential. You can make impacts by tapping the potentials, and businesses can make impact by, harness the value of smartphone sensor data. And yes, that will be it. Thank you.